Good afternoon, everybody, and welcome to my class on Experimental Design 1, STA 3108 in particular. So for those of you watching from any part of the world, welcome to my class, and for those of you in class, welcome. So let us quickly begin from where we stopped. A quick recap on what we did previously. I remember in my last class that we had introduced ourselves to experimental design, and we passed through several things we ought to know about experimental design and ended with mentioning what we can call the basic principles of experimental design. Please take note that these principles are not restricted to the three we mentioned in my class. You understand me? So that you don't think that that is all about it, the principles of experimental design. On the internet, if you go looking at the internet or through the internet for um, principles of experimental design, you may find elements like control added to the list. So it goes beyond three. You may not even find blocking there. You may find elements like manipulation also put into the list of basic principles of experimental design, but I added the word basic to just know that there are more, but we are considering those three. So when you go to the internet for sources and you see principles of experimental design, you will find more than those three. But we are considering those three as the basic principles of experimental design. Now, that was one thing I talked about in my last class, right? Another thing I discussed in my last class was it is not enough to say the basic principles of experimental design we shall be considering are randomization, replication, blocking. What are these principles? Why do we call them principles of experimental design? Among several reasons, one thing that is common to these principles of experimental design is the fact that they help you minimize or eradicate errors in the experimental setup. You get me? So if you know nothing else about the basic principles of experimental designs or the principles of experimental design in general, know that all of them in one way or the other, in one strategy or the other, do one common thing. They reduce experimental error. Is it clear? Now, based on that, let us quickly continue this class by defining each of them we've mentioned. So the question is, what is randomization? We need to know. What is replication? We need to know. What is blocking? We also need to know. And not only do we need to know their definitions, we also need to explain those definitions. So in this class, we will wrap up our first topic by explaining those things. We will now move, once we are done with that, we will move quickly into discussing the properties of what we call a good experimental design. So not every experimental design setup is good enough. So what property would make you disqualify an experimental design, and what property will make you embrace an experimental design as being a good experimental design setup? We are also going to look at that in this lecture. Okay, so let's begin quickly. So we will start with randomization, everybody. Randomization. Randomization. I hope it's clear there. Okay, so randomization involves the assignment of experimental units in a treatment so okay, better put, I think we should just go with randomization involves the assignment is, let me correct this, assignment of experimental units to treatments under a specified factor. Okay. Now, it is not enough to write this down. On this side, when I put up a definition, please, I'm going to come over here. to explain that definition. Is it clear? So that it becomes vivid what you are actually writing. Now, if you remember very well, we had discussed in my previous class, for those of you watching from any part of the world, please check the link to the first class in the description below, okay? So that you can actually follow the class from the very start to this present time. Now, we had discussed factors, we had discussed treatments, and we discussed what we call levels or replicates, right? And to each of them, I told you that factors are the variable of interest. And in my class, my previous class, I told you that a factor, for instance, could be the weights of students in a particular department. And in that department, we have, if you say the weights, you are considering the weights of students in a particular department in any institution at all. For instance, the department where we are, statistics, okay? Certainly, you would have so many students in that department, but each of these students are categorized naturally into different levels. We have the 100 level students, 200 level students, 300 level students, 400 level students, as it were in this case, because it's a 4-year program, right? Now, if you now segment all the weights you would get into those 4 levels, 100 level, 200 level weight, 300 level weight, 400 level weights, you will come to realize that you would have what we can now refer to as treatments, because treatments will now be levels under a certain factor of what? Interest. Is it clear? Now, in each of those treatments, take note of the fact that in each of the treatments, you would have measurements or observations of weights. You would have weight observations under treatment 1, weight observations under treatment 2, weight observations under treatment 3, and weight observations under treatment 4. Am I right or wrong? Now, take note again, because we are going to be considering 2 instances. Take note of the fact that the weight of all the weights you may get under treatment 1 may not be the same number of weights you get under treatment 2 as it is in this case, because the number of 100 level students admitted may not be the same as the number of 200 level students who were admitted previously. You see it? For that reason, you may have unequal number of weight observations under each treatment. That will give rise to what we will subsequently see as an unbalanced case. You get me? Where the number of observations in each treatment are not the same. Okay? For the next instance, we shall be looking at the balanced case. So if you have under each, let's assume that in year 1 we have 20 students, year 2 we have 20 students, year 3 we have 20 students, and year 4 we have 20 students, such that for each of those treatments, we would have 20 weights. That would amount to what we would call a balanced case. Do you understand me? But if you go naturally the way we are, such that the number of students in each level are not the same, you will end up seeing that the treatment will contain observations that are not the same in number. Okay? Now, based on that, those observations you have in a treatment can be called levels of that treatment, otherwise known as replicates of that treatment. Why are they regarded as replicates? They are regarded as replicates because they constitute a repetition of the basic experiment. The experimental activity in this case is give me a year 1 student, a 100 level student, give me a 200 level student, a 300 level student, and a 400 level student, and the activity involved will be for me to take their measurement. You see it? So if you go one instance, taking the measurement of the students, a student per treatment, or a student from one treatment, it will be the base. That is what we call the basic experimental activity. You get me? Now, if you take that activity again and again, it will amount to you having more observations under the treatment. And for that reason, if you come from that angle, you will now see those observations as replicates. Do you understand me? Because they are repetitions of the basic experimental activity. So that is the angle from which you can see it as replicate. But on the other angle, you could see them as what? Levels, because they constitute the different stages of repetition of the experimental activity. Okay? Now, I want us to look at this and explain something. I'm going to write something underneath this, but to start with, let us see what randomization means. When we say randomization involves the assignment of what? Experimental units to what? Treatments under a specific factor. So let's look at it this way, based on what I explained earlier on. So look at it this way. Let me start this way so that you can actually. So there is a factor of interest. There is a factor of interest we are calling what? Factor of interest X, right? Now, underneath this factor of interest X, whatsoever it is, we are now taking treatments. So I'm calling treatment 1 X1, treatment 2 X2, treatment 3 X3, and treatment 4 X4, assuming that X is the weight of students in the 4 levels. Now, look at it this way. Where randomization comes in is this. You see, that brings me to what I'm going to be writing next underneath this. Remember, we said that the basic principles of experimental design are those principles that ultimately do one thing, which is reducing or eradicating what? Errors in experimental design. Now, how does it do it? It is not enough to say they reduce what do you call it? Errors. How? Now look at it this way. Now you know this now represents 100 level weights, 200 level weights, weights of 300 level students, weights of 400 level students, right? Now let's assume in the first instance that in each of these levels we have 4 students, implying that we are going to have what? 4 weights. Is it not so? Per level. Now, randomization has to do with how you take the weights. Which out of the students for the first level, that is this treatment level 1, there are 4 students in that class. Who do you take first? Who do you take second? Whose weight do you take second? Whose weight do you take what? Third. So the weights that will go into this are what we refer to as what? Experimental units. Do you understand me? So experimental units will go into each of these what? Treatments. Now, it is only fair statistically that if you want to reduce any form of sentiment, that you pick each student and take their weight randomly. Now let's move away from weights and look at what do you call it? Each level and something to be assigned to them, like what we could call it a scholarship or a benefit, so to say. Now, if you want to do, some people will devise means like first come, first serve in trying to apportion. Let's say certain monies were apportioned to each level and the monies were to be given to the students, such that if you come first, your money is bigger. If you come last, your money is smaller. Do you understand me? Now, if the activity is such that who comes first takes a bigger portion and who comes last takes a smaller portion, you know very well that sentiment may come in if you are the one during the apportionment or the sharing, because you would want to now start considering where you come from and what students in that class come from your area, so that they can benefit better. Do you understand me? You may want to start considering how close you are to certain students such that they benefit better than those you are not close to. As such, if you start using sentiments to assign experimental units to each of these treatments, you will be maximizing or increasing the tendency of making errors. Do you understand me? So in order to reduce that error, eradicate it or minimize it, it is best you go with what? Randomization. Do you understand me? And that's where the principle of randomization comes in. So at the end of the day, whoever goes in first will be the first observation in the first treatment. All the observations here, they are values. This x is a random variable, so it assumes values, small x, right? So every observation that x will assume will be what? Small x, small x, small x, small x, small x. Now, at the end of the day, all the variables that go in here, all the values that will go in here as observations will be, in the first treatment, all of them will be x1 observations. All the observations that go in here will be what? x2 observations. All that go in here will be what? x3 observations. That is, if you are taking treatment first and what? Level second. This is a vertical setup. Now, all the what do you call it? Levels will now be, this will now be the first level in observation or in treatment 1. The second level in treatment what? 1. The third observation taken in what? In treatment 1. The fourth observation taken in treatment 1. You see it? Now, we are saying that even though looking at these variables or these values, you would think that they enter in that manner. No. This x1 randomization means that the x1 could have been, look at this class now. Let's assume that there is A, B, C, and D persons to go in. This, at the end of the day, this x1, x11 could be D if you randomize, and x13 could be A, x12 could be B, and x11 could be C. You see it? So randomization means no sentiment-based selection of the experimental units, no bias-based assignment of the experimental units to what? Treatment. You get me? So I hope that is clear enough. Now, what two types of errors? We said in any experimental design setup, there is what we call experimental error. And we say that experimental error is made up of two parts, two basic parts. What and what? Two errors will make up what we call experimental error. So randomization as a principle, randomization as a principle of experimental design is one, as a principle of experimental design, is one that helps to reduce or eradicate systematic error. You see it now. So the main target of randomization is to eliminate what? Systematic error. So experimental errors are made up of systematic errors and what? And random errors. Okay? And the attention of randomization is targeted at what? Systematic what? Errors. Is it clear? Now, next comes what do you call it? Replication. Replication. So replication refers to a repetition of the basic experimental activity. So when you repeat the basic experimental activity in an experimental design, we call that principle what? Replication. Is it clear? So replication is one that helps to reduce random errors. It helps to reduce what? Random errors. For example, you see these women who sell things, who sell fruits. In Lagos, they will shout, buy your sweet orange, buy your sweet orange. And you, when you tell them, come, drop the orange on the table, I want to purchase some. So you ask them, you may ask them the question, are your oranges sweet? They will tell you yes. Test one now. They will give you one. You test. Now, even as they've told you that all of them is sweet, when you test one, there is this inner what do you call it? Inner mind of you as to whether the rest are like the one you've tasted if the first one is actually sweet. Do you understand me? Now, you would want to test again to confirm. And the more you test, the more certain you become. Do you understand me? You will notice that the more you test, if you test one, you will be unconvinced. If you test the second one, you will be slightly more convinced. But the more you test, you start testing 3, 4. That 3, 4 you test, if the taste is as sweet as the ones you tasted previously, it will now put in your head something called consistency in the level of what? Test. I don't even understand what I'm saying. So what we are saying is that replication is that principle that comes as a result of repeating the basic experimental what? Activity. In this instance, the basic experimental activity is the first one you tasted, which was enough to make judgment, right? But because if you ended at that first stage, it will give you an unconvincing judgment. Why do you think in an electoral process we would always want a president to rule for 2 terms? The first term could be challenges he met did not make him perform very well. But the second tenure, for instance, a good example is Donald Trump. Donald Trump ruled only for a period of 4 years, right? And there are some people who judged him as being, what do you call it, his presidency as being good enough. Some said it was terrible. Do you understand me? Good. Now, another opportunity with another 4-year period, one can now say, if he does the same thing for those who felt he was bad based on their reasons, if he repeats those same things that made them judge him as being terrible, if he repeats it again, there will be consistency and they will conclude that he is actually bad. And those who said he was good, if he repeats what they felt were good about his presidency, if he repeats them again in these next 4 years, they would judge him as being a good president. You understand me? So why are they doing that? It is because the more you repeat, in this instance now, his 4-year presidency period is what they consider as an experimental unit, the basic experimental activity, such that if he repeats it again, if he goes for another 4 years, it's just like taking another observation. Do you understand me? And as such, it now makes room for what we call replication. And that would reduce random errors in the system. Is it clear? Now, so we had already stressed the idea of replication previously by showing you those observations. I explained why those observations you take. Repeating the basic experimental activity amounts to replication, right? Now, I hope you follow what I'm saying. Good. So let's now go to the next one. The next one we are considering is the principle of what? Blocking. Right? So we are considering the principle of blocking. So the question is, what does blocking do? So blocking is a principle which refers to the grouping of experimental units into what are referred to as blocks. The intention here is to minimize random errors. To minimize random errors also. Is it clear? So now let's see. Let me give you an example of how blocking can be achieved. So I hope we can conclude this first topic in this class, right? So we are not too far from the end. Let's conclude it and know that in the next class we begin the second topic. Okay? But I hope everybody follows what I'm explaining. Good. So which do I wipe off? Replication. So let's now see. Let me give you a little illustration as best as I can to just show you what blocking is all about. Please look up. Now see, let's assume that let's go back to that example we gave. Let's go back to that example we gave. So this is treatment 1, treatment 2, treatment 3, treatment 4. Now, I could block by categories such that let's assume that we had weights ranging from 10 to 40 kilograms. Now, I could block, if without blocking, I could have, if numbers had been assigned randomly, I could have here, I could have, what do you call it? I could have had weights like 17, 25, what do you call it? 33, 40, for instance, in this one. I could have here 20, 17, 19, 35. I could have this. Now, I could decide to introduce a blocking parameter or condition such that the blocking condition is first, in every treatment, I want 2 blocks. And in each block, one block will be for weight less than, less than 25, for instance. And the other block will be for weight greater than what? 25, but less than 40. Less than or equal to what? 40. You see it? Now, as soon as you do that, this setup automatically changes. Meaning that you would now have, in this case, you will have 2 blocks containing 2 observations each. In this one, you would have what? You would have 2 blocks having 3 observations in one and 1 observation in the other one. Do you understand me? And the whole essence of blocking is to put them in what? The observations, the experimental units in a particular treatment, in what? In what we call blocks. Is it clear? So it could also be a means to minimizing random errors. Okay? So if let's consider this now in particular. There were 2 treatments. Let's consider this as before blocking and after blocking based on this yardstick. Before blocking, this was 17, 25, 33, 40. Experimental units assigned randomly to treatment 1 and experimental units assigned randomly to treatment 2. After blocking, based on this now, I will have 17, 25, 33, right? Making what I will refer to as a first block. And in the second block, I will have what? 40. In this one now, I will have 35 as the second block, right? And in my first block, I will have what? I will have 20, 17, and 19. You see it? Okay, that being said, let's move to the next. I hope everybody understands that. The next thing I want us to consider is the subtopic procedures in DOE. What does DOE mean? DOE mean design of what? Experiment. But I'll prefer you put it in full, please, in your own note because of space. Procedures in design and analysis of experiments. So we'll write the following. The following are sequential procedures to follow or to implement in the design and analysis of experiments. 1. The first thing you do in the design and analysis of experiments is to recognize and state the problem. Is it clear? To recognize and state the problem. See, when you guys get into final year, the department will require, as part of your course at final year, you take STA 4000 or 400, STA 400, as it may be. And what is expected is that you carry out a research and document your findings. In a research activity, what begins, before you begin a research, there is something called recognizing a problem. There is no research you carry out that is not meant to tackle a problem. You understand me? So it is a problem that gives rise to what? A research. So the first stage of the design and analysis of what? Experiment is one similar to that case, that requires that you recognize a problem that needs to be addressed and you can clearly state the problem. You understand me? Some people recognize problems, but they cannot state the problem. So recognition and stating the problem is the first stage in experimental design. So we'll put the recognition of and statement of the research, the design problem. That's number 1. Number 2, once that is done, you have to now make good choice of your factors and levels. Choice of factors, treatments, and what? And levels. So question is, now that I have recognized the problem in the experiment that will give rise to the experiment, now that I've also been able to state the problem, the question now is, what should be the suitable factor or factors? Like the one I talked about earlier on weight, and using each level, undergraduate level, as my treatment, and the observations themselves as my levels. You will notice that I was able. The next thing is to, once you are able to recognize and state your problem, your choice of factors, you must be able to tell what should be the factors, what are the treatments, and what are the levels. The third thing that follows after that will be to be able to select your response, what we call a response variable or a response. So you must be able to select a response variable. Number 4, you must be able to choose a suitable experimental design. So, choice of suitable experimental design. Please, subsequently, I'm going to explain this. Eh? Are you listening? I'm going to explain this because, see, it is under here, a problem is presented to you in experimental design, and you say, come, this particular problem is to be attended to using factorial designs. This particular one is to be attended to using fractional factorial design. This one here will be good with a nested design. This one here will be good with split plot design. This one will be good with split plot design. This one will be good with response surface design. Maybe a central composite design, a box and Benken design, a placket Bowman design. All these I'm mentioning are different designs. And these designs are based on choice. But when choosing, it must be in relation to the demand of your problem. You understand me? It is how your problem is stated that determines what design is suitable for it. Is it clear? So if you don't choose carefully, you may be using a factorial design for a problem that requires a split plot. You may be using a split plot design for a problem that requires a factorial design. Is it clear? So that is what we mean by choice of suitable experimental design. Number 5. Once you are able to choose the suitable experimental design, the design will help you know how to get your data, and once that is done, once you can choose a suitable design, then you can perform what? The experiment. So step 5 requires you to do what? Performing the experiment. So step 6, I believe I can wipe this off, right? So in step 6, once you are done performing the experiment, what next? You now go into data analysis in step 6, and you round it up in step 7. So in step 6, VI, you go into what? Data analysis. And in step 7, you can now conclude and make recommendations. Conclusion and what? And recommendations. Recommendations. Okay? So, those are put together the, what do you call them? The procedure for implementing the design and analysis of what? Experiment. Now let's go to the next thing, which is properties of a good design of what? Experiment. Properties of a good design of experiment. Now, what are the properties of a well-planned design? Number 1, a well-planned design will have the absence of systematic errors or experimental errors in general. Experimental errors. And by that we mean both systematic and what? Random errors. Okay? Which of course we've told you different ways to reduce or eradicate them. Is it clear? Number 2, a good design must have high measurable precision. So don't come and tell us that this design, the accuracy in my design was high. The question is, how did you measure it? I don't even understand me. So you don't just tell us that based on what I did, it was high. How did you measure it? So it must have high measurable what? Precision. Is it clear? 3, a good design, a good experimental design must have wide range of validity. So number 3, we say what? It must have what? Wide range of what? Validity. Number 4, the design of experiment, if it is good, must be what? Simple. So another property is the property of what? Simplicity. And number 5, if the design is good, it must have calculable calculable means of reliability. Okay. Now, the last discussion is analysis of experiment. Remember what we've been talking all along was under what? Design of what? Experiment. Okay. So this is the last thing I want us to talk about to call our discussion off. Okay. So now for analysis of experiment, when we say we've talked about design of experiment, does not mean we've exhausted design of experiment. We've not even scratched the surface. So we have just introduced ourselves to what design of experiment means, and we are also going to introduce ourselves briefly to what is embodied in the language analysis of what? Experiment. Is it clear? So that's what I mean. I don't mean we've done design of experiment. No, please, far from that. Please, can I wipe this off? So let's now round up this lecture with analysis of experiment. Let's round up the class with analysis of experiment. So please take note, our next topic will be completely randomized design. Completely randomized design. You can write that after this class. Analysis of experiment. Analysis of experiment. Analysis of experiment embodies the following. 1. Data collection and processing. So when you tell somebody that in experimental design you are analyzing the experiment, it means you are one of what you may be referring to is data collection and what? Processing. 2, when you tell somebody that you've started analyzing an experiment, the next process may be computation of statistical tests. Statistical test. You may start test in plural, please. Here is where you start. That is after collecting your data, you may start performing t-test, ANOVA, chi-square, and all of them are different statistical tests. Do you understand me? So that is also embodied in the analyzing process or analysis process. Okay? So the third and final thing in the analysis of experiment is the case of interpreting or interpretation of results for the experimenter. Interpretation of results for the experimenter. So these are the 3 major items that embody what we call analysis of what? Experiment. So to analyze an experiment embodies data collection and processing. To analyze an experiment embodies computation of statistical tests such as t-test, ANOVA, chi-square, all types of statistical tests that may be required in your analysis as it were. And then to analyze an experiment implies interpretation of results for the experimenter. Is there any question? In the absence of any question, thank you for your time. I remain Dr. John Efiongusen. So please subscribe to the channel, like the video, and do share the video. I'll see you in my next class, which will be on completely randomized design. So the link to this class or the first class on this particular lecture is in the description below. Please be a member of my community. Okay? So I have a YouTube community. All you need to do to join my community is to click the join button and follow through. I'll be waiting to see you there. Thank you very much.